Hello and welcome back to lecture 2. So we're going to continue now by talking about colour constancy. We've already covered lightness constancy, and colour constancy is essentially the same phenomena, but now we're interested in how different wavelengths of light are affected, not just the overall brightness. So colour constancy is the perception of constant surface colour despite changes in illumination and viewing conditions. In other words, if you view a banana, for example, you could view that banana under a wide range of viewing conditions and you will still perceive the banana to be yellow, regardless of the light source that's being reflected off that object. I mean, we know this is generally true. We experience life under lots of different lighting conditions. So depending on the light bulb indoors or depending on the viewing conditions outdoors, there will be a wide range of different frequencies under different viewing conditions hitting the object and being reflected. But we have this constancy. We're not aware of colours dramatically changing, even though the wavelengths of light being bounced off those objects can be dramatically different under different conditions. So human colour constancy is not perfect, but it's pretty good. It's remarkably good. We see the same when different and different when the same. So we see this. We see an orange or a banana as having the same colour, even though the viewing conditions are radically different. But also we can see things as being different when they're the same, and I'll show you an example of this. Okay, so if you look at this image here, if you look at the square in the middle here of this face and this face, you can tell that this one is brown and this one is orange. But if I put a mask on, you can see that the actual colour in terms of the light being emitted by the screen is identical for both of these squares. Okay, but remember, your brain is interested in what is it out there that's causing this activation in my eye. Okay, so under these lighting conditions, your brain's conclusion that this square is brown and this one is orange is correct. Your brain is taking into account the fact that this side of the cube is in shadow and this one is in full brightness. So your brain is telling you what the correct colours are, even though the wavelength that's being bounced off the cubes is identical. So at some level, your brain is having to take account of the illumination of the object. So if we look at what's going on physically, it's very similar to what we saw with lightness. So again, we're using the same terms, illumination, reflectance, and luminance. But this time, we're interested in the amount of light at each frequency, not just the overall light. So if we look at the illumination spectrum, this is the amount of light coming from the thing that's illuminating the scene. Okay, so this could either be the sun or this could be a light bulb. So the illumination spectrum is showing you how many photons are being emitted at what frequency. Okay, so here this is quite a flat spectrum, so a fairly even number of photons at each wavelength. The reflectance spectrum is the proportion of light reflected at each wavelength by the object. Okay, so this is the internal physical property of the object that doesn't change. Okay, so this object is going to reflect frequencies where there are peaks, and it's going to absorb frequencies where there are troughs in this spectrum. Okay, so this object, whatever it is, it's reflecting wavelengths very strongly in the order of around 480 nanometers, but you can see it's absorbing a lot of the frequencies at around 550. And then luminance is the amount of light reflected at each wavelength. Okay, so this is what would be being received by your eye or by a camera. So you can see that the reflectance spectrum is acting like a filter. It's taking the light that's being admitted onto it or being shined onto it. Excuse me. It's reflecting some wavelengths strongly and absorbing others, and then what you get out being reflected by the object is this luminance spectrum. Okay, so the luminance, what we actually perceive when we look at the object, is a combination of both the illumination spectrum, the wavelengths being admitted by the light source, and the reflectance spectrum, which wavelengths are being absorbed and which ones are being reflected by the object. So if we look at our fruit bowl example again, let's just pretend we're looking at the banana. Okay, in natural light, or if you look at natural light or light being emitted by a light bulb, they're going to have wildly different illumination spectrums. The reflectance spectrum is remaining the same because the physical properties of the object are not changing. So this is our filter, if you like. And then we have the luminance spectrum, what's actually being emitted from the object and hitting your eye. And you can see in natural light, it's this is a very flat function. So what you're seeing in the luminance spectrum is quite an accurate reflectance, reflectance of the reflectance spectrum. Okay. Remember that the object is only capable of reflecting wavelengths it's actually being exposed to. And you can see that here. If you look at the light bulb, it's not emitting many photons at these lower wavelengths. So you have the same reflectance spectrum, but you're going to have a wildly different luminance spectrum. The object is going to have wildly different wavelengths coming off it under these two different lighting conditions, but you don't notice a dramatic change in the colour of the object. You still perceive the banana as being yellow. So how does your brain do this? In some way, it's having to recover this reflectance spectrum. It's having to do some reverse engineering so that you see the colour as being constant. Okay, you constantly see the banana as being yellow. So you must somehow have to take into account this illumination spectrum. And we think this, together with memory, which we'll look at in a minute, we broadly think this is true. Exactly how this is done is still somewhat of a mystery, but we do know that the brain takes into account the surroundings, the ambient lighting conditions that it's viewing the object under. And we can see this with this example here. This by an experiment by Land in 1983. He presented these Mondrian patterns, and they are illuminated by different coloured lights. Now, when the whole pattern was visible, and people looked at a single patch of this, when the whole pattern was visible, and people stared at a single patch, they didn't perceive it changing colour. Now, it's a little bit difficult to demonstrate on a computer or a projection screen, but I'll try and show you what I mean. If you stare at this green patch here that I'm illuminating with my cursor, I'm going to change the lighting conditions. What I'm actually going to do is change the surrounding border here. And I just want you to see whether you notice this green square changing colour in any dramatic way. Okay, so I'm just going to change, and again, and again. Okay, I would guess that you're perceiving that green as not altering that much. It is changing a little bit, but you're still perceiving it as being green. Okay. However, if we only view a single patch without the surroundings under exactly the same lighting conditions, then you should perceive the colour changing. So so now this is the same patch that you saw before, and I'm changing the lighting conditions just like it did before, and now you notice quite a dramatic change in colour. And this is exactly what was happening back here. So your brain is taking account of the effect of the surroundings. It's taking account of the characteristics of the illumination in the scene. But again, exactly how this is done is not well understood. And some recent phenomena have suggested that the assumptions we make about the lighting conditions, particularly when the situation is ambiguous, can differ quite dramatically from one person to another. So you may remember a few years ago the viral phenomena of that dress. Okay, so this is the original photo on the left, and when people looked at this, they either perceived the dress as being white and gold, or they perceived the dress as being blue and black. And it's almost, I find it impossible to see the opposite. I see this as being white and gold. I can't see it as being blue and black. So there's something that's hardwired into my brain that's making a top-down process that's making an assumption about what the lighting condition is here. So my brain is assuming that the lighting condition is shifted towards the blue spectrum. But if you see that it's blue and black, you're assuming that the light source is shifted towards the red spectrum. Now, the reason why this is working is because this photograph here, there isn't enough context, there isn't enough of the image for it to be unambiguous about what the nature of the light source is. Okay, so it's actually wearing the dress itself. And this has been photographed under white lighting conditions, so there's no ambiguity. So everybody viewing this should see the dress is actually blue and black. Okay, so as well as the effects of the surroundings, we also have the effect of colour memory. So we obviously have prior knowledge of the typical colours of familiar objects. Okay, everybody knows that a banana is yellow and a strawberry is red. Everybody knows that the order of the traffic lights is red, orange, and green. So we have this top-down memory of objects, which, if we're looking at a familiar object, will help us in terms of colour constancy. And there's some neat experiments that have shown just how strong this effect is. So this experiment by Hansen et al. In 2006, they presented images of grey fruit against a grey background. This isn't the actual stimuli they use something slightly different to this, but this will serve as an example. So when the fruit and the background were set to identical shades of grey, observers still perceive the fruit to be slightly coloured. So they still perceive the fruit here as being slightly yellow, these grapes here as being slightly purple, and these carrots here as being orange. Again, these aren't the stimuli that we use, so it probably won't work for you. And in actual fact, when people had to set the colour of the banana to be grey, they actually set the colour to be slightly bluish, the opposite of yellow. So the top-down memory of bananas being yellow, in order to cancel that out, they have to shift the colour of the banana slightly into the bluish spectrum. And the same was true of opposite colours. So if they were adjusting the colour of a lemon to be grey, they would actually shift it slightly into the blue spectrum. So you can see there's a very strong top-down effect of our memory for colour of familiar objects. If the object is unfamiliar, then this isn't going to help you. And you can see this works in some quite dramatic ways. So you should still perceive the strawberries here as being red, even though the strawberries here are actually grey. Okay, I've zoomed in on the strawberries here. So these ones actually are red, but these ones are grey. But your top-down knowledge of strawberries being red is overriding the actual sensation coming into your eyes. Okay, it's changing your perception, your top-down knowledge of strawberries being red. Okay, so in conclusion, colour memory helps us to accurately perceive colour under different illuminations, together with our perception of the surroundings or assumptions about what the light source is.